Hmm.
So maybe Ravi, we could start, and I think
Yeah,
people will
sure.
join in slowly.
Sure.
Uh, so let's go ahead. So
Hmm.
today we are honored to have a very distinguished particle physicist with us, Professor Rabindra Mohapatra of the University of Maryland. Over the past half a century, he has made very many important contributions in his field, and describing them all will probably take this entire lecture. So I'll have to keep it brief and touch on only some aspects of his career and research. Rabi, as we know him in a friendly way, Rabi obtained his undergraduate degree from Utkal University in Bhubaneswar, India, and master's from the University of Delhi. He obtained his PhD in 1969 from the University of Rochester, working with Robert Marshak. Subsequently, he held postdoctoral positions at Stony Brook and Maryland, a professorship at the City University of New York, and a visiting professorship at the Max Planck Institute for Physics. Since 1983, he has been a professor at the University of Maryland. Rabi's most important contributions have been in the field of neutrino physics. In his famous series of works with his student Goran Semyonovich, he developed the left-right symmetric unified theories, which are then spontaneously broken to the observed theories of electroweak interactions with parity violation, and they also made a prediction of the neutrino mass. This forms an important part of the so-called seesaw mechanism for the origin of the neutrino masses. Rabi's work has deepened our understanding of left-right symmetric models of unification, and more generally, he has contributed importantly in the field of grand unified theories as well as supersymmetry. Today, Rabi will talk to us on the subject of dark matter and mirror worlds. Over to you, sir. It's a great pleasure to have you with us.
Thank you very much, Tejinder, for inviting me to give this talk. And it's a pleasure to meet all of you. And let's see how it goes. Okay. Well, the title of my talk today, can you hear me?
Yes, all clear, all clear.
And also the slides are clear.
Yes, yes.
Okay, great. The title of my talk is Dark Matter and Mirror World. And what I would like to argue is that the dark matter particle is not one of the familiar particles that people have been saying, like the supersymmetric neutralino or the axion or something like that, but rather it is a particle which belongs to a companion universe, which we call mirror world. And we will see that several puzzles of dark matter physics can be solved if you adopt this point of view. Okay, so what I would like to do is, let me see how the outline of my talk is something like this. Let me just try to arrange it a little bit better. Okay. So the outline of my talk is first I give an overview of some of the dark matter properties, and then I will see why it could be suggesting that dark matter is a mirror particle that I will be arguing afterwards. So then I will introduce what is the mirror model and what are the basics of the mirror model, and then I will talk about a problem which plagues the modern dark matter physics, which is why is the dark matter content of the same order as the baryon content. The dark matter content, as you all know, is about 5 times the baryon content. And why is it that they are so close? And certainly the supersymmetric model or the axion model do not give any explanation of this very important property. So then I would like to outline a scenario, which is one of the several scenarios in this kind of model, where the baryon and the dark matter coincidence comes out as a consequence of the mirror world picture. And then one of the predictions of this theory is that the dark electron could be dark matter. And we will see some of the consequences of this. And please stop me anytime you want in the middle. Okay, so let me just start with some of the overview of the dark matter properties, which all of you know, so I will be very quick on that. Let's just go through it. So here are the many evidences for dark matter from astrophysics and cosmology. On the left, right, I hope you can see my cursor. This one is the galaxy rotation curves. The flattening of the rotation curves sort of suggests that it's not all baryons, but it is a lot of dark matter in the galaxies. This one is the bullet cluster, where you see these are the baryon part of the cluster, and this is the dark matter part. The blue part is the dark matter part. So that because it has very little interaction with matter, it sort of goes ahead, and the baryon part stays behind because it is sort of has to slide through it. So that takes work. And the last one is the cosmological evidence from the angular spectrum. And you can see the peaks correspond to baryons and the dark matter. That all of that gives a dark matter content, which is in this slide, which tells you how the dark matter sort of divides into different, the dark energy content of the universe divides into different parts. There's the dark energy, which is roughly 73%, which nobody understands what it is or what its origin is. And secondly, there is the cold dark matter, which what we'll focus on, and that's about 23, 24%. And these are all baryonic matter, which are 4 to 5%. So you can see that between the baryonic part and the dark matter part, it's almost of the same order. There is a factor of 5 difference, which we would like to explain. So the dark matter puzzle, dark matters have been pursued for the last, I don't know, maybe 30 years or so. And there are several, which has not been, of course, discovered, otherwise you would have heard about it. But there are many puzzles that dark matter physics gives us. First of them is that despite many evidences for dark matter in cosmology and astrophysics, all laboratory searches, underground searches for it, the so-called WIMP model, to that has come up negative. And here is a picture of what is the sort of current status of the WIMP nucleon scattering cross-section, the spin-independent part, and the WIMP mass. And here you can see the WIMP mass goes all the way from a TeV, from a GeV to almost 10 TeV. And then here it is, these are the cross-sections, spin-independent cross-section. And you can see the limits are going down and down and down. Okay, they started over up here. Now they're going down to almost 10 to the minus 48 centimeters square. Now, if it kept going down, you could simply say that, okay, now I build a bigger machine or bigger detector and I can see these things. But that's not quite true, because what happens is that below a certain region, mass, certain cross-section, there is something called neutrino floor. That means once you come down to this level, neutrino interactions from the atmospheric neutrino, the solar neutrino and all those things, they will start creating background which you cannot distinguish. So therefore, we are pretty much reaching the limit of what one can detect in terms of dark matter from the experiments in the conventional way, that is underground experiments in different places. But of course, there is still some region to be covered, so that they will keep going around for a long time. So this is one puzzle as to why, in spite of such strong evidence for the dark matter, we don't see it anywhere. The second puzzle is the dark matter content and the matter content of the universe are of the same order, as I have been emphasizing. So you can see this, the omega dm, which is the rho dm over rho critical, is about 5 times the rho matter over the rho critical. This factor of 5 is intriguing, and one would like to understand why this is the case. Okay, so we will call this almost same order of magnitude a dark matter baryon coincidence puzzle, even though they are not exactly same, but almost similar order. And why is it so? That we will call dark matter baryon coincidence puzzle. And the point is that could these two puzzles, the fact that you haven't seen the dark matter in any experiment, and the fact that the dark matter and the matter are of the same order content, are these two could related? Then there are some other dark matter puzzles that also people have been focusing a lot of attention lately on. That is the dark matter just a collisionless particle? That means it has no collision with each other at all, or it may be self-interacting. In other words, as they pass by each other, they get deflected. Okay, and that's a big difference if you have self-interaction or if you don't have self-interaction. The collisionless dark matter simulation, for example, the so-called Navarro-Frank-White simulation, has led to halo density. That means the density of the dark matter, which goes like rho, some constant, divided by the radius from the center of the galaxy outward, and r is some number. Okay, the distance from the center of the radius. Now you can see one property of this is that as r goes to 0, as you go towards the center of the galaxy, the density becomes singular. In other words, there is a Cauchy kind of property, of the dark matter density. However, what observations have shown is that if you are looking at a dwarf spheroidal galaxy or some low surface brightness galaxy, the cores are, the centers are much shallower than the simulation seems to suggest. So that's one of the problem. Why is that way? Why is it that way? If the dark matter is collisionless, like the axion or like the WIMP, why is it not that the centers of the galaxies are not more cuspy than what has been observed? The second puzzle, which is known as the missing satellite problem, is that if you do the simulations, what you find is that the number of the galaxies, the number of the number of the galaxies as a function of mass goes like m to the minus 1.9, which means that if you are looking at smaller satellites or smaller satellite galaxies, then there should be more of them than what you observe. And that puzzle probably is slowly getting less and less, giving less and less tension, but still that is a puzzle that one would like to understand. Now, essentially motivated by these two puzzles, in 1999, Spergel and Stein had proposed that dark matter may have self-interaction. In other words, it's not just a particle by itself, but it has some interaction. And there could be this is called SIDMs, self-interacting dark matter, and this could resolve these problems. Okay, so I hope I made it clear. The dark matter that people generally consider nowadays has several problems with it. The fact that it has not been seen, the baryon matter coincidence puzzle, and then the self-interacting possibility. So all these things, if we can have a framework where all these properties are explained, that should certainly be interesting. Okay, and that is what I would like to argue today. So there is, once I talk about self-interacting dark matter, it's not that this interaction is arbitrarily strong, because if the interaction is arbitrarily strong, then the galaxy will become spherical but not elliptical. Okay, so therefore you must have an upper limit on the cross section, and also there must be some lower limit to give some observable effects. Okay, so
Just
typically,
a quick question, sorry.
yeah.
This self-interaction is something like a fifth force, or is it a standard? It's not.
It is a force between the dark matter particles, so it could be like fifth force, it could be like similar to the standard force. What I would like to argue is that it's very similar to the standard model force that we see, but it's a different standard model force. In other words, with that force, the dark matter does not interact with normal standard model particles. It just
Oh,
interacts
oh,
with itself.
thank you, thank you.
Okay. So here is an upper limit from different papers, and similar bounds can also be obtained from the. So this is without taking into account any of the velocity dependence of the cross section. But if you take the velocity dependence, you also get similar bounds, and also you explain other things like the rise of the uh, galactic rotation curve and so on. So that's quite interesting actually. So the self-interacting dark matter has been a focus of many attention of many workers recently in the dark matter area. So the bottom line of all this is that we need something more than simple collisionless dark matter particle to explain the dark matter. Okay, collisionless, something collisionless like the WIMP or the axion or stuff like that. But maybe something a little more complicated, but hopefully not too complicated that we can't say anything about it. There are also other facts about dark matter which are important. And the dark matter, whether it's WIMP type or whether it's whatever type it we talk about, there can be two varieties of dark matter. One is called symmetric, another is called asymmetric. So what is asymmetric and what is an asymmetric dark matter? These are probably very well known, but I'm just repeating it because all these things I will use in my final part of the talk, which gives you the mirror dark matter with baryon and dark matter equivalence. So the possibility that dark matter is asymmetric means the following. Suppose you have a dark matter and the anti-dark matter. So this is the dark matter and the anti-dark matter. If their content is different, in other words, if dark matter content dominates over the anti-dark matter content, that is called asymmetric dark matter, which was proposed in 1985 by Nusinov. And this has again taken over as another side of the dark matter physics. On the other hand, the standard WIMP picture or the axion picture there the dark matter is its own antiparticle. Okay, so in other words, whatever the dark matter is, its antiparticle is same. And of course, in the supersymmetric case, it's a Majorana particle. In the axion case, it's a neutral particle. So that these properties are automatically satisfied. Okay, so therefore, this is another thing that one has to worry about. What I would like to argue today is that it is probably an asymmetric dark matter and not this dark matter symmetry. Okay, so that also distinguishes the conventional dark matter candidates from the kind of picture that I will be talking about. Okay, so let's move on. So now I am coming to the dark matter and mirror world. So what is the new picture that we are proposing? We have been working on it for a while. There are a lot of people working. I'm not the only one. So I'll try to give a review of what are the basic ideas of the mirror world and how the dark matter comes out of that picture. Again, please stop me whenever you have any issues. So the idea that we have been very fascinated by is, could the dark matter be residing in a companion universe? The companion universe is in the same space-time as we are in, but it's a different set of particles, and they interact among themselves and not with us except through gravity. Okay, so here is why we think that could be a possibility. The first puzzle could mean that only interaction between matter and dark matter is extremely weak. The first puzzle meaning why we are not seeing dark matter in any experiment, or we may never see a dark matter in any of the laboratory experiments, which is unfortunately a little bit depressing for the people who are engaged in it, but there are other people who support them, so that's quite fine. So the interaction between the dark matter world and our world may just be only through gravity, in which case you will never have enough strength or enough juice to give a signal in the conventional experiments. So that is what is preventing us from seeing it in the lab or in the underground setups. The second one is that the fact that the omega dm is about 5 times the omega matter. It could be suggesting that there is some similarity between matter and dark matter. It may not be two different particles. If they are similar, then there is some chance that you will have the dark matter content is of the same order as the matter content. Okay, so if there is, now that could happen if there is a symmetry, and I will argue that there is a particle physics symmetry which suggests this kind of a picture, which was advanced long ago. Okay, so these are the two motivations, and now let's try to give some details. So the mirror world for dark matter is all the suggestive of the mirror model, where all known matter and forces are accompanied by a mirror sector with identical particle and force content. In other words, if you have we have the standard model where we have particles like quarks, leptons, and W bosons, G bosons, and all that. Higgs bosons have all of this stuff. And suppose there was a duplicate of this picture, but the duplicate being everything is different in the other world, then that will be the mirror world. And that was first suggested in the famous Li Yang paper on parity violation. They were so unhappy with the suggestion that they threw out one or two sentences which said that maybe there is a symmetry which relates to another group of particles where the right-handed weak interaction is taking place. And that is why the parity is conserved, and not because we don't see it, the parity is not absolutely violated. So that was, as you may probably know, when Li and Yang gave their theory, Pauli was extremely antagonistic to it, and he said, God is not left-handed and all that stuff. So they threw in one sentence in their paper. I don't know whether it was in reaction to a referee report or what they did, but there was certainly a little bit of that. But that was developed by several Russian physicists. And then more recently, it has been picked up by several of us in the context of neutrino physics. And I think this has more to it than neutrino physics or dark matter physics. There is a whole new set of things that one can discuss with this. Now,
Could I
once
ask you, sorry to interrupt you.
no, that's
What the thing that you call the right-handed weak interaction,
right.
why can it not be ordinary gravitation as we know of in general relativity?
As far as we know, gravity does not distinguish between left and right. So it could be if there is a picture where the gravity is just focused on right-handed particles, but we know that the pure left-handed particles also have the same gravity strength. But that would be an interesting way to go. I don't know if I have never thought about that possibility.
Okay,
That's
yeah.
interesting.
So some research is going on experimentally also to investigate if gravity is chiral like the weak interaction at a
Right,
fundamental
right,
level.
right. Yeah,
Yeah.
I think that would be an interesting thing to pursue, but unfortunately, I don't have anything interesting to say on that.
Thank you. Thank you. Please go ahead.
Sure. So now, once you have this mirror world picture, you have one world for us, the standard model world, and then there's a mirror world. Then if you take the lightest particle of the mirror sector, that has nowhere to, that cannot decay because there is nothing below it in its mass. And everything that is below its mass could be in our sector, so it doesn't decay. And therefore, this is the stable particle and it can be dark matter. And this is the picture I will adopt. And this picture also, of course, since there is a whole new world with similar interaction as the standard model interaction, all these mirror sector particles, including the dark matter, there will be interaction between them. For example, if the mirror particle is the dark electron, then there will be dark electromagnetic force. So everything in the mirror sector we'll call dark. Okay. So for the electrons is a mirror dark matter. Then it will be a mirrored dark force between the electrons. So that's the self-interaction force. And all these kind of ideas in separate contexts have been investigated by different dark matter physicists. And the subject of this talk, the rest of the talk will be to how to understand the omega dark matter is of the order of omega matter in this picture. Okay. And this, there have been previous works on this. We did some work, and then there is other people in our group here, they have done some work. But what I will focus on is the last paper right here by this Nobu Okada and myself. But that's not the only picture where you could implement this idea. Now, the first question you can ask is why even Lee and Yang thought about this mirror world, or why mirror world in general? Well, there is a parity puzzle in weak forces. We know that all forces, the strong forces, the electromagnetic forces, and the gravity forces, as far as we know, are all parity conserving. But the weak interaction is certainly maximally parity validity at low energy. So the question is it really genuine or is it an illusion? In the sense that because we are at low energy observing beta decay, we see parity violation, or if we go to really extremely high energy, will we still see the parity violation, or the theory will be parity conserving? And there are 2 points of view. The first one is the left-right symmetric model, which came out around 1974-75, where what happens is that you take the standard model gauge group SU2L cross U1, and then extend the gauge group to SU2L cross SU2R cross U1B minus L, where B is the baryon number and L is the lepton number. And it turns out that in this theory, you can break the SU2R cross U1B minus L at a higher scale, let's say 5 TeV, or let's say 10 TeV, or let's say 100 TeV. We don't know the scale, of course. That depends on what is the mass of the right-handed W boson. But once you break the theory to U1Y, then that gives the standard model results at low energies. But once you go to extremely high energies, which we can achieve in the accelerators, then and colliders, then you can see the SU2 plus U1B minus L. That will be a proof that this is the point of view that is taking place in the parity situation. But on the other hand, what Lee and Yang proposed long before us is that there may be a different world. We have our world, and then parity takes us to a mirror world. That means that our particle, mirrored particle, our force, mirrored force, everything, our Higgs, mirror Higgs. So once you have this picture, then of course, when we have weak interaction in our world, there could be the other counterpart to the weak interaction, the right-handed weak interaction, the mirror world. So once you do the parity, which takes you from one world to a mirror world, then the whole theory is parity conserving. So this is a very different kind of theory, and I will pursue this kind of theory today. So the difference here is, of course, it's the same particles in the parity symmetric world, but here it's a completely different set of particles, and one of these particles could be dark matter. There is no such situation in here that can be dark matter because everything in here essentially decays. And there is a picture called seesaw mechanism which comes out in this kind of picture, and that sort of gives the neutrino mass and also gives all kinds of new signals for the left-right models. But I will be talking
Just
about
a,
this today.
sorry, just a quick question.
Yeah.
The SU2R cross U1B minus L breaking, are we sure that that cannot be at the electroweak scale itself?
Yeah, there are a lot of arguments that it cannot be. One of them is, for example, we have measured the K long K short mass difference very precisely. Okay, there is a very precise number. There is little bit of error in that. Now,
Mhm.
if you take the SU2R cross B minus L scale at the weak scale, then that result will completely be destroyed because
Okay.
the right-handed ones contribute to the flavor changing neutral current. And
Okay,
similarly,
great.
also
Thank you. Thank you.
similarly also BB bar mixing and all kinds of things.
Mhm. Thank
So,
you.
so that is the limit from those kind of processes, the flavor changing neutral current processes, is sometimes something around maybe 5 to 6 TeV now.
Okay.
And
Okay.
of course, collider bound is also around that.
Mhm.
Okay. So here is a picture of the mirror universe that I will be talking about today, which is the Lee Yang picture extended by many people over the years. Okay. So let's look at this side. This is the standard model, SU3 color, SU12 cross U1Y. And you can see the familiar quark doublet, the singlet up quark doublet, singlet down quark, left-handed lepton doublet, right-handed electron. And you can see that there is no right-handed neutrino here. Then you go to the parity partner, the mirror world, where will denote everything by a prime. So there is a corresponding to QL, there is a QR prime. The corresponding UL, there is a UR, there is a UL prime, and all that stuff. So these are the mirror world, and they have the opposite helicity to the fermions of our world. And then what we will do to build this, so this is the basic part of the mirror world picture. But when we build models, of course, you have to put in some new particles and some new ideas and stuff like that. So what we do is we put in some singlet neutrinos, right-handed neutrinos, like NRSR. So these are two singlet right-handed neutrinos. Don't bother about the details because that I will never show you any of the construction of the model in the talk. So these are sort of broad picture that I'm painting. Now, one similarly, you can go to the gauge sector and you can see that you have got the W, Z, and gamma, and gluons, and all that stuff. They're the standard model particles. And then there are the prime mirror particles, is the W prime, G prime, gamma prime, and gluon prime. Okay, so you can see that there are different fermions, some constituents are different, and the force particles are also different. So these are the force particles of the standard model, and these are the force particles of the mirror sector. So you see that these guys interact only via the exchange of these prime particles. So therefore, this has no interaction with the WG gamma. So therefore, it will not scatter against the fermions or any detector will never see them. The only force connecting these two sectors is either gravity or if you postulate something else, this has been a super weak like the gravity level. And then, of course, we have got the Higgs boson, this is standard Higgs boson, standard model Higgs boson. There is a duplicate of that in the mirror sector. This is a singlet that we will do for model building, the singlet prime. And then there I will throw in something called the Higgs. There is a new particle which will do the baryogenesis. So this is essentially the entire content of the theory. So you can see that if you think about the parity symmetry, which sort of duplicates everything to that side, there are not that many new particles. There are two extra heavy fermions. Higgs boson we know exists, then the eta and the phi. And all so these are the four new particles, NR, SR, eta, phi. All the others are sort of parity duplicates of these. So once you have these guys, then you can write down your theory without doing any. Just close your eye and write down the theory. All the couplings are the same, that the particles go from one to the other. Okay, so that's all there is to it. And please stop me because this is a crucial slide where I'm telling you what are the real contents of the. I will not, of course, do any model building. I will not write any Yukawa coupling. I mean, not write any, but I will write some, but I'm not going to write down the details. So, for example, in this sector, the mass is generated the same way through the Higgs mechanism as in the standard model. And similarly, the neutrino mass will go through some variation of the seesaw mechanism using these particles that I will describe in detail. And then the
The
double, yeah.
the mirror fermions, except for the neutrinos, are the same as the right-handed fermions of the standard model.
No, no, no. The right-handed fermions are here. This is right-handed upward, right-handed downward. They're different
Hmm.
fermions by similar properties. You can,
Okay, okay.
okay.
Mm-hmm.
So the mirror particles are completely different. the mirror gauge bosons which mediate the force, so they are completely different.
Mhm. There's a quick question in the chat. Can
Yeah.
one rule out that the bosons are their own mirrors?
Bosons are, sorry.
Bosons are their own mirrors, he's asking. Like you have a mirror gauge boson W prime.
Mhm.
Question is, can W and W prime be the same or is that ruled
No,
out?
no, that is different. Everything is different because if W and W prime are same, then this should undergo beta decay to our particle, and it does not. There is no connection through exchange of
Hmm.
W prime from the. So these are so in other words, you can think of it as a completely disjoint world. The only
Hmm.
connection is gravity.
Okay, okay. And all these particles now for the mirror world exist in our 4D space-time.
Yes, they all exist in 4D space-time.
Hmm. Thank you, thank you.
Okay, so this is the general features. That is the same space-time, but their companion universe. In other words, in principle, of course, it's not probably happening, but in principle, you are sitting there right next to you could be mirror you or mirror Fermi or mirror whatever. Okay,
Yes.
so that's the duplication. So the same space-time, but a companion universe with the mirror world. The two sectors of the universe, there are two sectors. One is the visible sector and the other the mirror sector. This is called the mirror world. We'll call the mirror world. The two sectors interact only via gravity and possibly other ultra weak forces that you need for model building. But that's not, I will not use too much of that. So essentially for our case, the two sectors interact only via gravity and maybe through these heavy right-handed neutrinos or something, we'll see. So now you see that the way we have constructed the model, the lightest particle of the mirror sector can be dark matter because it is completely stable and it has nowhere to go. So it remains in the universe. The only question is how do we adjust its relic density so that we can fit the observations. Okay, so that I will discuss. So the first thing, of course, if you are an expert in cosmology, first thing you will do is you will tell me that this model is wrong because we know the BBN works very well. The Big Bang nucleosynthesis works very well when the universe has a temperature of 1 MeV. We are producing the helium, we are producing the lithium, we are producing the beryllium and all this kind of nucleus. And that one of the key requirements to fit data over there is that there must only be the known neutrino, the photon, and the electron-positron pair. Okay, so that gives the something called the number of degrees of freedom, which is the GBBN star. This is the required one, which is 10.75. That fits quite well with what we know. So the question is, in this model, you will immediately have a duplication of all those things. Okay. So if the temperature of the both sides were same, then you will have this the GBBN in this mirror world plus the GBBN of the standard world all add up to twice the G required. And that will completely spoil the success of BBN. That was realized many years ago, I think almost 30 years ago. It was pointed out by, pointed out by several of us as well as other people that it's not going to, we have to somehow suppress this G required from double its value to the almost the 10.75, which is what is required to satisfy the BBN requirement. And one way to do that is to just reduce the temperature of the mirror sector, make it cooler. Then since the energy density goes like T prime to the fourth, once you make it a little bit cooler, that is enough to satisfy the BBN. In fact, what happens is the temperature of the mirror sector of the universe is about half the normal sector. Then you are okay, you are doing fine because that one half to the fourth power is 1 over 16. And that's where our limits on the extra number. Inflation mechanism which is proposed here, or there are certain decay mechanism. So I will not go through all the details, but this is what actually is happening, one can do. The second part of the mirror world idea is that there can either be a symmetric mirror world, which means that you have a Higgs boson in the standard model sector, and I think there is another question in the chat. I don't know what it is. Let me take a look.
Shall I state
Oh,
the question because I'm the
yeah,
one that
please.
asked it? In fermions of the standard model come in both left and right-handed versions. In
Mhm.
what way is a mirror left-handed electron different from the usual left-handed electron?
That's a completely different particle. The mirror electron is a completely different particle. It's like a separate particle altogether. And it does not interact with our electron except through gravity. Gravity can pull it, but not nothing else.
I understand that, but the mirror electron, as I understand it, has essentially exactly the same pattern of charges. All the fermions have exactly the same pattern
Right,
of
right.
charges. It's
But this,
just that somehow there's two symmetry groups, and the you're just taking two sets of particles which are acted on by identical symmetry groups.
right. I think that's a
Okay.
very interesting question, and I'm going to address it a little bit later. But what you are suggesting essentially is the following. There is a U1 in the standard model and the U1 in the mirror sector. Couldn't the two U1s mix? Because that is allowed by gauge invariance. And if they mix, of course, there will be interaction between the two. But that puts in another parameter, which is the mixing parameter. And that leads to something called Milli charge. In other words, the dark matter will have a little bit of, tiny little bit of charge depending on this mixing. And then they will start interacting. But a priori, we don't have to put a Milli charge because if you have some kind of theory, there is a loop effect which gives a Milli charge, but in this theory that I have, there are no Milli charge effects. So in other words, the dark electron and our standard model electrons are completely separate, even though they have similar looking. The important word is the looking. The similar looking interactions, it's not the same interaction. So the
Yeah, I think maybe Rabi, could we rephrase the question? Andrew's question is following. What experiment could you do in principle to discriminate the standard model electron from the dark electron?
there are, if there is no photon mixing, no dark photon, mirror photon, dark photon, our photon mixing, then there is
Hmm.
nothing, no laboratory experiment can distinguish it. It has to be something cosmological.
So
Okay.
can I press on this a little bit? I
Yes,
mean,
sure.
should I understand that the coupling parameters of the mirror world are the same as the coupling parameters of the standard model? And in that
Exactly.
case, there would be mirror galaxies.
Yes, yes.
And one would surely see signs of mirror galaxies,
Yes, I
which I
think
don't.
yeah, you are anticipating some of my talk, but I think that's a good point. Point is you do expect, but you remember in the previous slide I showed something which is that the temperature of the mirror sector is much less. So therefore, that will completely affect the galaxy formation. That unfortunately has not been studied in detail anywhere. But one can give some hand-waving argument that if you have a temperature, lower temperature, then things happen differently in the cosmological evolution of the mirror sector. So that, and in fact, the galaxy you are talking about, we expect it to be bigger, and that will be the galaxy halo that we are talking about. So there will be
Why would
galaxy.
it have lower temperature?
That is a particle theory construction. In other words, it can be that the inflation reheating is lower in the second sector than our sector, or maybe there is some other particle physics property that's going on. I will describe another one, but there are many ways people have now figured out how to lower the temperature of the mirror world. But it's important. The BBN constant tells you that the temperature of the mirror world must be lower, at least a factor of half, possibly more. I hope that makes some sense. I mean,
Okay.
there will be galaxies, but they don't have to be exactly like our galaxy. Okay, so let me now come back to, if there are no more questions, let me come back to this slide. With the symmetric mirror world, you have got the two Higgs bosons have the same vacuum expectation value. So in that case, all mirror particles have the same mass as the standard model ones. And the asymmetric picture, the Higgs wave of the mirror sector will be higher than the our wave. In other words, this is 174 GeV. This probably is 10 TeV or even higher. Okay, so the particle masses in the mirror sector in this case will be higher. And this is the picture I will adopt because that picture is much easier to understand neutrinos and other stuff. And that picture also tells you why the omega dark matter is about 5 times the omega matter. So if there are any other questions, please start. Okay. Let me
Please
see.
go ahead. Please go ahead. Yeah.
Let me see what happened.
No more questions right now. Kindly proceed. Yeah.
Yeah, I'm just trying to see. My computer is stuck for some reason.
Not proceeding, is it? The slides?
Yeah, it's not proceeding.
Could you go to the navigation mode and then see or use that? Go back to the navigation mode
Where
where you
is
have all the slides showing on the left.
it's a participant chat, share, pause.
No, on your when you started the talk, all the
Mhm.
slides were showing on the left, and then you came to this sort of full screen view.
Let me try to keep pressing. I'm just pressing different buttons, but it doesn't seem to move
I
anywhere.
think the best would be to stop sharing and share again.
Okay, let me, you're sharing screen. Let me stop share.
Yeah.
Okay, then let me share again. Yep, now it works.
Yeah. Yeah. Go ahead, please.
So there are two kinds of mirror models now. One is the symmetric mirror model and the other one is asymmetric. So before I go to the asymmetric one, which will be the focus of my talk, I just wanted to make one interesting thing that has happened in the symmetric mirror model. It was pointed out in that in the symmetric mirror model, since the neutron of our world is same as the same mass as the neutron prime, mirror neutron, there can be possible oscillation between these two if there is appropriate interaction connecting these two particles. Okay. So what happened is that once that theory was developed, a new interaction was proposed. There is an experimental search going on at different places, which sort of has tried to discover an prime oscillation. Of course, they haven't found it yet, and there are limits. Sorry, there are limits on the different parameter, the oscillation time versus the mass difference between the n and prime. They are all related. And you see that this shaded region is ruled out. Okay. And there are several experiments going on in the Oak Ridge National Laboratory, the ILL in France, and the PSI in Switzerland, and so on. There are some other consequences of this symmetric mirror model, which is that if you have a neutron star, which is a big object is full of neutrons, then if the neutron goes to a mirror neutron, then there could be some heating of the neutron star, and that has been analyzed by several groups, including us. And what we find is that for some regions of the photon-photon prime mixing, there can be some heating of the neutron star, and by looking for the temperature, measuring temperature of different neutron stars, one can possibly check this. But on the other hand, if you have a higher gamma-gamma prime mixing, which is right here, the photon-mirror photon mixing, and if the mixing is sizable, then that will not, you can make this effect weaker. And the second thing is that if n prime doesn't decay, it just stays stable, then of course you could have a neutron star with mass which is root 2 times smaller and with a larger mass. Okay, so there are different consequences. And again, this is something which is a very active field and several groups are working on it. But on the other hand, I will focus on the asymmetric dark matter model, where what we have is the mirror symmetry with all the couplings are same, but the vacuum expectation values are different, so that the quark masses of the mirror sector are bigger than the quark masses of our visible sector. Okay, so the mirror quarks and leptons are heavier. This is my preferred scenario. Okay, so let me just proceed with that. So what happens in this kind of an asymmetric scenario is that if you look at the evolution of the strong coupling, then asymptotically the couplings are same because it is mirror symmetric. But as you go down in energy at some point, the right-handed top quark decouples and then the strength goes up and so on. So the weak interaction becomes stronger. And the lambda prime QCD becomes 5 to 10 times the lambda of QCD, depending on the mass of the top quark, mirror top quark. So this is a very interesting thing because this automatically predicts the baryons of the mirror sector are heavier. And of course, the leptons are automatically heavier because the wave is bigger. But the baryons, depends mostly on the lambda QCD. So therefore, if the lambda QCD prime is much bigger than lambda QCD, then you can have a heavier baryon. So this is very important for dark matter, because this model predicts dark matter of the mirror sector, which is about 100 times bigger or so. Okay, so now let me try to quickly focus because my time may be running out, but so the baryon dark
But
matter.
take your time, please. We no hurries. We let the speaker go
Okay.
to extra time, and also we asked you a lot of questions. So please, no
Okay.
time constraint. Yeah.
Okay, great. So now I'd like to focus on the last part of my talk, which is the baryon dark matter coincidence, or why dark matter abundance is 5 times in matter abundance in this kind of a theory. So this is a recent preprint that we put out a couple of months ago. So to understand the matter-dark matter connection, of course, we have to know how matter is generated and how dark matter is generated. And I will be talking of a picture of dark matter relic density, which is asymmetric dark matter, so that the dark matter is not by WIMP annihilation type, the standard supersymmetric type model, but it is the same way the matter abundance. In other words, as you know, the matter abundance comes from three of Sakharov's conditions. You have baryon number violation, or lepton number violation, or you have CP violation and out of thermal equilibrium. So what we'll argue is that in both sectors, you have some version of somehow these three conditions are satisfied. So the matter, you have a matter, more matter than antimatter, and then more dark matter than anti-dark matter by similar mechanism. Now, once you see that things are similar, then you have a hope of relating them. Okay, so that's what we are planning to do. So there are different mechanisms for ordinary baryogenesis. For example, you can look at leptogenesis. There is something called electroweak baryogenesis, which happens at low scale. Then there is something called Affleck-Dine mechanism, and then there is something called post-Speller. There are different mechanisms. There are probably some more that I'm not writing here. But what I will be using is this one, which is known as Affleck-Dine mechanism. And I will try to argue that in this picture, what you have is a field which also does inflation, it does baryogenesis, it gives rise to similar order of magnitude for the matter abundance and the dark matter abundance and all that stuff. Okay. So this is my favorite mechanism right now. So if you want to explain the dark matter baryon correspondence, then you must have a mechanism that gives roughly the dark matter abundance of the similar order. As I will never say equal, because equal is always some fine tuning is involved there. But similar order of the baryon matter asymmetry. So this dark matter, anti-dark matter over n gamma, nb n gamma, and this is nb over nb bar over n gamma. So now, given this one, if the dark matter is a few times the proton mass, then it solves the puzzle. And we saw that in the asymmetric picture, the few times is very natural. So that's why I prefer the asymmetric picture of the mirror world. So what will
The dark matter is the lightest mirror particle.
Right.
So would that naturally be the neutrino, or it could be something different?
No. Yeah, the neutrino is the lightest, but that will never be the neutrino. It will always be either electron or a neutron. Mirror.
Okay. Thank you.
Yeah. So what is the Affleck-Dine leptogenesis? This is a very detailed study and a lot of people have worked on it. So I will just give you the broad features of the model. First, what it does is the model will have a very weakly broken lepton number on both sides of the mirror world as well as our world. Then there will be a complex field which has got lepton number. And then what happens in this model, this is a very important line which tells you that in the, in the early universe, by either quantum fluctuation or gravity fluctuations or whatever, the real part of this complex field is different from the imaginary part of the complex field. So this is where the CP violation, which is part of Sakharov's requirement, is really introduced. So these two are different and they are not equal to zero. Okay, so that's the input essentially. It's like the CP phase. Then once you have that, then you can calculate the lepton number asymmetry in this theory. Then what you find is that the imaginary part of the charge density is the charge density in quantum mechanics. That's not equal to zero if this condition is satisfied. And then we couple the phi field to lepton number, as I said here. Then when phi decays, you have a lepton. This asymmetry in the real and imaginary part translates into lepton asymmetry. So I'm just saying a lot of things which are detailed, but this is the broad picture of it, this broad set of ideas as to what is being done. So the asymmetry in the phi, which is the real part, imaginary part asymmetry, gets transmitted to the standard model leptons. That creates a lepton asymmetry. This asymmetry is converted to the baryon asymmetry through these phalerons, and that's the usual way of leptogenesis. Or if it doesn't convert, then of course you have got leptons as the dark matter. Okay, so there are 6 or 7 steps here, which are kind of very crucial, and I will not go through too much detail because that becomes extremely complicated. But essentially, these are the broad picture. You have lepton number violation, which is very weak, so this is one of the Sakharov requirements. This one is the CP violation requirement. Then it follows that from this you generate an asymmetry in the leptons, and which then gets converted to baryon through these phalerons of the SU2 group of both sides. Now I'm getting into too many details, so if you can just switch off for the next 2-3 slides if you don't want to listen to this part. So phi is also an inflaton, and the way it does inflation is you take non-minimally coupled to gravity. So you have a function f, which is a function of phi square over m Planck square. This R is the Ricci tensor, and this is the Lagrangian for this complex scalar field, which I call the Affleck-Dine field. So what you have is a mass for this part, and then there is a lepton number violation, because you can see that if phi is lepton number, phi square will break lepton number. And this is lepton number conserving. So this is the usual lambda phi square, lambda phi fourth term in the scalar field theory. So this A we define as some parameter epsilon, which is epsilon times some m phi square, because this is mass dimension m phi square. So the epsilon is much less than 1. Okay, and the phi determines the phi evolution. So this part is depending on how strong this is, it will determine how the field is evolving from the early universe to now. So what you do at the next test to understand inflation is you go from Jordan frame to Einstein frame by a wild redefinition. And that gives you inflation, because essentially what you do is Jordan times this F, the non-minimal coupling part, it becomes Einstein metric, and then the potential becomes this, the usual Jordan potential that I wrote in the previous slide, divided by the 1 plus this phi square over m square whole square. Then you can see that if phi is much bigger than the Planck mass, then this is a constant, because this is lambda phi fourth up there, and this phi fourth down here. So as phi is, for huge values of phi, like m Planck over some zeta square root, then this gives rise to a constant potential, and that is inflation, of course. Now, of course, as the field evolves, the phi will certainly become less than m Planck over square root of zeta. The inflation will end, and then just the normal evolution of the phi will continue. And that is where something interesting happens. You can see that the phi has got phi 1 plus I phi 2, the real part, imaginary part, and this is the evolution equation for the complex field. So the V prime, that's the potential, and I have rewritten this explicitly. And when you rewrite this explicitly, because of the epsilon term, because of the imaginary, the epsilon split the masses of the real and the imaginary part, you can see that there is an M1 here and M2 here. The real part evolves according to one mass, the imaginary part evolves according to one mass, so therefore the original splitting is preserved as the particle evolves. And in fact, you can write a leading order solution to these equations, which looks like this. And that in the end gives rise to an asymmetry between the scalar fields. Okay, so this is a little bit technical stuff there. But bottom line is that in the beginning, if you had a difference between the real and the imaginary parts of the complex field, that is preserved as you go down. Then what you do is, now you have an asymmetry, and what you do is you take the asymmetry, and you have, in your Lagrangian, you have a coupling of the complex field to the right-handed neutrinos of the hour sector, and then left-handed neutrinos of the mirror sector. Question? Okay. And then there is, of course, the usual term between the right-handed neutrino and the lepton doublet and the Higgs, right-handed in mirror sector coupling of this. So you can see the couplings are the same, and the form of the interaction is also same. There is a plus, there is no absolute epsilon here. Now when m phi is for h and phi decays to n, so this h is not the Higgs, this is the Hubble constant. So when the mass of the Affleck-Dine field is the order of Hubble constant, then the phi decays to Nn by this coupling, and decays to N prime by this coupling. And the decay, this decay transfers the asymmetry in the phi to the right hand and the heavy particles, the neutron. And when these new heavy particles decay to leptons and Higgs, lepton prime and Higgs prime, that asymmetry is transmitted to the standard model and the mirror sector. Unfortunately, this is a little bit technical. I hope I'm not going too fast, but probably I am. But so once you have, so the basic idea, just to repeat, is that in the beginning you have got an asymmetry between the real and the imaginary parts. That asymmetry gets transmitted to the leptons and the leptons of the standard model sector and the leptons of the mirror sector. And then there is some more technology, model building work that goes on. So once you have this kind of a Lagrangian, you can write down you can add some soft breakings and you can write down the neutrino mass, and it turns out that the neutrino mass, after this is done, the coupling of the complex field to N has the following form. It is for the standard model sector, it's a much bigger coupling than than the mirror sector. So therefore, what happens is that the mirror sector becomes cooler. So this is a key part, because I remember I told you that the mirror sector must be cooler than the normal sector. And this is what tells you that this is cooler, because the delta is much less than 1. So now you look at this and you see that this is the key line in this slide, which is the mirror sector temperature, reheat temperature over the normal sector reheat temperature is delta, which is a very small quantity. But luckily, this is related to the branching ratio of phi to this, and this leads to cooler mirror sector. But also this leads to something measurable in cosmology, which is the amount of dark radiation. Okay, so this is what I will come to now. So just to summarize, you have real and imaginary part both not equal to 0, and then there is a lepton number asymmetry. That lepton number asymmetry through these decays goes to the standard model and the mirror sector, and the spherons of NL to B, NB, and mirror lepton to mirror baryon. So now, of course, what you do is you just take the mirror lepton ratio, and that's the same as lepton, visible lepton times the branching ratio. This we know, this is the standard NB over N gamma. So therefore what you see is that if you want to get omega dark matter equal to over omega baryon is equal to 5, then all you have to do is that gives you a relation between the mass of the baryon prime to the branching ratio. And that's roughly, we calculated this in our theory, it is 4.69 divided by the branching ratio. So what we're talking about is, if this branching ratio is about 1%, then the mirror baryon should be about 469 GeV. Okay. And this, of course, happens if the mirror temperature, reheat temperature is bigger than the electroweak prime of the mirror sector. But if it is less, then the spherons of the mirror sector have already decoupled. The lepton asymmetry has no way to get into baryon, so that remains lepton becomes the dark matter. So we have a two benchmark set of points. I don't think you really want to see these. These are just to make sure that there are parameter ranges where we get our theory to work. And then in this theory, you can calculate the neutrino mass, which is given by this formula, where this is the coupling. These are the waves of the different two sectors, and M is right-hand neutrino mass. And this is small. This is like a seesaw mechanism. And this is small. Of course, here the neutrino is a Dirac particle, so there is no neutrino as double beta decay. So that's another prediction of the theory, that you should not see neutrino as double beta decay, for which there are many experiments going on now. So now finally, as I said, there is the branching ratio. I think that I see two more charts. Let me see what there.
We can come to the comments in a discussion session. Kindly complete the talk. Yeah.
Okay, great. Okay. So you can calculate the dark radiation amount, which is given by this parameter called delta and NF. And we calculated that. What we find is that this is related to the branching ratio. So you see that the Planck data or the CMB spot data, which will come, they essentially tells you what the delta NF phase is, and once given that one, you can predict the branching ratio from this relation, the branching ratio to the mirror sector. And that branching ratio will then tell you what is the mass of the dark matter. Okay, so now current constant is the branching ratio is less than 4%. So that means that the T prime over T is about half. Okay, and that's fine. That agrees with BBN calculations. Oh, I see. Once I go to this, okay. Yeah, I think once I go to the chart, somehow it decouples.
Mm-hmm.
Okay, so this is just a graph which tells you how things are going. So as you see that as branching ratio increases, the okay, so this is an important point. Remember, I'm talking about an asymmetric dark matter, which means that the symmetric part must somehow deplete because there are U prime bar, so they must annihilate each other. That puts a constraint on the theory, and that is this picture reflects the constraint. In other words, if the branching ratio is more and more, then there is a chance that they will annihilate more and more, and then of course the asymmetric part dominates. If the branching ratio is less, then the asymmetric and the symmetric parts will compete with each other. That's not a good situation. So therefore we have a lower limit on the branching ratio, which is about 0.001, and that tells you that the delta N effective is about 0.06, so which is sort of not far from something that the CMBS4 experiment or CMBHD experiment can look for. And then there is just a few remaining slides. The self-interaction also, the mirror electron, if the mirror electron is a dark matter, there is self-interaction and it solves the core cusp problem due to thermalization. Then there is we don't want the self-interaction to be too strong, so we expect this to be about 0.5 centimeters square per gram. And then the forms dark stars by gamma prime bremsstrahlung, that has been looked by several people, that if you have a mixing between the photon and the dark photon, then that can form dark stars which through gamma prime bremsstrahlung cooling, that may be observable somehow in the form of the reionization or something. So then the last couple of slides, one is that you can do a non-minimal extension. As already I started discussing, that if the gamma and gamma prime mix and the gamma prime has a mass, then also it satisfies the BBN constant, and people have tried to fit the G minus 2 in this picture, and that gives to some constraints on the mixing parameter and the mass of the photon. And of course, this gives rise to some energy injection, and which can alter the 21 centimeter signal, which these people have looked at. Okay, so I think that's the end of my talk. We just summarize. So the question is, what we are looking at is, what is the nature of the dark matter particle? Does the fact that the matter and dark matter contents of the universe are of the same order hold a clue to this? And what we are arguing is that the mirror universe or the parallel universe model provides an elegant explanation of this puzzle via neutrino masses. The dark matter is very much like ordinary matter, and that's something interesting. And the model prediction is the dark matter mass should be around 100 GeV, and also a lower bound on the delta N effective, which is about 0.08 or something like that. So we should wait for CMBS4 and CMBHD to give the results so that one can compare this theory, at least put some constants on this theory. Okay, thank you very much. I think I'm done.
Yeah, great. Thank you, Rabi. Thank you very much for a very clear and enjoyable talk. The talk is now open for questions. Please use the raise hand feature. There are two comments which I will read out. And then first one is from Andrew. He's just trying to understand the implications of the mirror model. As I understand it, there is mirror baryonic sector with strong interactions, and the mirror hydrogen atom is 5 times heavier than the usual one. There should be mirror counterparts, and I would expect they gravitationally cluster together. But globular clusters contain no sign of dark matter. Am I understanding correctly? That's Andrew's question.
Yeah, that's a detailed structure formation question. I'm not sure so much has been looked into that, how the globular clusters form or how they. I think what generally people have talked about, and that at least that's how much I know about it, is that the dwarf spheroidal galaxies and the low surface brightness galaxies and so on, which have less baryon content than the dark matter, they sort of are more easily explained in this mirror picture. The globular cluster, unfortunately, I don't know how to answer that question. I don't
Andrew,
think
you want
anybody.
to add something? Andrew, you want to add something?
No, I'm just trying to understand what the model is. My understanding is that the mirror matter and ordinary matter are gravitationally clustering together, but clearly there are definitely places where that isn't happening. And the globular clusters came to my mind because they're rather large concentrations of matter. I could imagine that solar systems would maybe separate mirror solar systems, but globular clusters, that would be a little more difficult, especially as they formed very early in the universe. I don't see how you could get some separation of globular cluster and mirror globular clusters.
Yeah, thank you very much. I think that's a very interesting question. Unfortunately, I don't do any simulation or anything like that. I just do broad particle physics picture, and that could be something for the simulation people to look at and see whether they can, what they can say in this model about the globular clusters. I think there has not been too much work on the simulation of mirror models, but the people have looked at models like just instead, just strip everything out, just put in an electron and a dark photon and their interaction and see how that applies. I'll try to check the literature and see if there is any result on that. But unfortunately, I don't know anything on that part.
Okay, then thank you, thank you. There's a comment by Matej Paushik. Matej, could you kindly, if you are able to switch on your audio, comment on your comment because you have given some references. Are these in response to Andrew's question?
We don't hear you. Please unmute your microphone.
Yeah, Matej, are you there? If you please unmute your microphone. Yes, yeah. Hi. Please unmute your microphone and let me see. Can I do that for you? Ask to unmute. You are muted, is it? Oh yes. Oh, he's muted, unfortunately. Okay, so we'll wait if he gets his audio because I don't quite understand what these references are for. And
now I see the switch for our audio. So you can hear me now, yes?
yes,
Oh, yeah.
yes. Please go ahead. Please go ahead.
By mistake, I switched, I turned on the video, but then I did not see audio because it was out of the screen. Now I somehow found it. So please give me the question. I can also give video, but I am not in the
Yeah,
right.
what I was saying,
I can put video as well. Yeah, okay.
yeah, you have put in the comment
Yes.
few references and yes, an explanation is in the This is an explanation for what? For Andrew's
Yeah,
question?
unfortunately, in the meantime, when I was typing, somebody else interfered. So I just
Okay,
explanation
I get it.
to the question how mirror particles can be distinguished from ordinary particles if they are both right and left-handed. And this comes naturally from Clifford algebra, as it was explained in my old paper in physics letters B, and then I reported about this at a conference in Moscow I think in 2013.
Yeah, I know. I am familiar with one of your papers on mirror model long ago, but I have not. I have to look at your physics letters paper to see. But
Yeah,
this is the point. But broadly, I can answer it for us. The mirror particles are completely different. So if you are looking for a collider signature, you will not see it. If you are looking for a there are three ways to search for dark matter. Make it, break it, and shake it. There are three ways. So if you, none of these ways will essentially show you mirror matter because they're totally disconnected. If you have a dark photon mirror, dark photon, normal photon mixing, then there can be some very weak signals in cosmology, astrophysics. For example, you may have some stars which will, mirror stars which will shine but very weakly. So you will have very faint stars in the sky. So something like that one could do. So the unfortunate thing about this kind of model from collider point of view is that you cannot really get a signal for this kind of, unless there is a strong photon gamma photon mixing, but that's already ruled out by supernova and BBN and stuff like that. So this is a sort of very weakly separated sector, very weakly connected to our standard model particle. But it just explains this is dark matter and possibly some of these puzzles of dark matter physics, such as the dark matter baryon coincidence and some other stuff that I told you about. The self-interaction, which comes very naturally in this model, looks to me like there is a lot of evidence for self-interaction of dark matter now. So I think that these are the kind of things I'll worry about.
Okay. Thank you. So the next comment is from George Sparling. I'll read it out. As I understand it, there are at least two features that the mirror and the ordinary universe have in common: gravity and Planck's constant. This presumably would have to be justified by the existence of some grand unified theory that would unify both the universes. Is there a candidate for this? I suppose for the grand unified theory. By the way, I like any unifying group that builds on the triality concept. Could there be two mirrors? Oh, okay. Our universe, a mirrored universe, and another mirror. Yeah.
Yeah, I mean, in principle that is possible, but then you have to do this BBN constraint, repeat it again for the other universe. And I'm not sure that people have really looked at that. I mean, I think the simplicity is sort of the main thing in this model. If you have two mirrored, two pictures, two sectors to the universe like this, one can certainly do a lot of stuff. But of course, in principle, there is nothing which tells you that you cannot have a third universe. So that's the not really an answer, but that's my response to the second part of your question. The first part is, yes, people have looked at the grand unified theories of this type, which is now these are SU2, SU2 prime, SU3, SU3 prime. So the unification is generally in SU5 cross SU5 prime or SO10 cross SO10 prime. These kind of ideas have looked at, and I'm not sure that there is anything drastically new that happens. I think usually, typically what happens is that if you do detailed construction, and some of these theories do lead to the photon mixing, dark photon mixing. So and that's an interesting feature anyway. But in those theories, you can predict the dark photon mixing. But other than that, I don't think there's anything else because these two sectors are sort of always completely separate.
More questions, please. So, Ravi, I had a couple of questions. Firstly, in the early part of your talk, when you reminded us of the left-right symmetric model, which had a SU2R cross U1 B minus L. Now it's my ignorance. Why did we pick up a U1 B minus L corresponding to U1 weak hypercharge? What is the physics there? Why does it couple to B minus L, this U1?
No, what happens is the following. Once you go to left-right models, the SU2 cross U1 expands to SU2L cross SU2R cross U1 B minus L. Then the hypercharge of the standard model is equal to I3R, the third component of the SU2R algebra, plus B minus L over 2. And that actually fits the charges very well because you can, for example, if you look at the B is the baryon number and L is the lepton number, and that really works quite well actually.
So if we wanted, sorry, no, you finish, please.
No, that's okay. Yeah.
If we wanted it to be something other than B minus L, would that be ruled out or
No. It will not be ruled out in the sense that, for example, there are theories where the B minus cell does not contribute to electric charge. That's possible. But those are kind
right,
of,
right.
yeah, there is
Because
more.
I was thinking you mentioned constraints saying that uh, breaking of SU2R cross U1 B minus U B minus L will not happen at the electroweak scale. Suppose I had something other than B minus L, I don't know what,
Oh, yeah.
then can I engineer? What is nice is, if the left-right symmetry breaking is such that everything happens at the electroweak scale, then there's something nice about it, rather than having the right-handed symmetry break on a higher scale and the left-handed later. It would have been nice if both the left-right symmetry breaking scale is the electroweak scale.
I think in the usual versions that I'm familiar with and I've worked on, that doesn't happen because that will give rise to a lot of problems with flower changing neutral currents that we know
Hmm.
extremely good data on. But
Okay.
if you to a different version, the two constants. First thing is that the beam, suppose you had something like SU2L cross U1 times SU2R cross U1 prime. Okay.
Mm-hmm.
When you want to relate the U1 to U1, when you want to impose parity, then U1 gets related to U1 prime. And in that,
Mm-hmm.
again, the same problems come up. The Prabodhani neutral.
So the kind of thing that I am looking at with my collaborators, the U1 prime
Mhm.
couples to square root of mass.
I,
The analog to the weak hyperts are essentially a square root of mass plus some analog of weak isospin. So that's a new kind of coupling we have been considering. It would be very nice for us to understand if that is constrained by flavor changing neutron currents. I mean, I'll send you the papers because you could tell us if our model is already ruled out. I mean,
sure. I will be happy to look at it.
great. Thank you. Thank you. My other question is more philosophical. Um, Suppose we say that there's no dark matter, but a fifth force amongst baryons,
Mhm.
which is such that it in the outer regions of galaxies or under suitable circumstances in cosmology, it dominates gravity just to mimic dark matter. So I'm just replacing dark matter by what you I would have called a U1 prime actually. Uh, Ordinary baryons are having a new force that we were not aware of, which behaves so as to fit the rotation curves and fit the CMB. I've never understood why this did not attract attention amongst particle physicists, and why do we say it's a new particle which gives additional gravity? Why not a fifth force between standard model baryons?
Yeah, I'm not sure people have looked at that kind of issues that much. When the only thing that you are, I'm sure, familiar with is the Mond theory. But that,
Yeah,
I'm not sure this U1 prime will lead to a Mond theory.
yeah, that's
But,
what
but
we
it
are
will be,
looking at actually. That's what we are looking at.
yeah, but it would be interesting to see if there is a U1 prime, whether there is any particle physics constraint on it, like the
Yeah,
Flabergen.
So we sort of called it dark electromagnetism and dark photon. It's massless. It means something different from what is usually meant by the dark photon. So we're
Yeah,
trying.
I'd like to read the papers and then maybe,
Okay, great. Thank you. Thank you. Yeah, that's all I wanted to know. Yeah,
sure.
yeah. More questions, please? Ashutosh, you curious to know your thoughts. You have been attending the previous dark matter talks. Ashutosh has left, is it? I
Yeah,
think yeah,
yeah, I'm here. Hi, Ravi.
yeah. I was thinking you
Sorry,
have
I had
been at.
another meeting a bit late. How are you?
Why don't I see you now? Do I? Yes. What I was thinking, you have
Yeah,
attended our previous dark matter talks and
yes.
Mount talks also, and you saw this discussion with
Hi,
Rabi.
Asutosh.
Any new thoughts? As I mean, I keep coming back to this question of why there's this so much of difference of view between the Mon community and the dark matter community. I mean, I understand that we don't have a good theory underlying Mon, and we don't have a good relativistic Mon, but those are current limitations in the same nature that we are investigating new dark matter candidates. That theory is being developed like Ravi described today. So, yeah.
By the way, I had one question. Does Mond explain the CMB angular
Uh,
spectrum?
with like this Cordis and co-author, these Czech co-authors did develop a model, a scalar tensor gravity model, which can fit the CMB. But of
Yes.
course, I would say that we have to see how stable it is from the quantum field theory point of view. So,
Mhm.
in principle, my understanding from listening to Moti Milgram is that yes, you can make a model which fits the CMB, but we would like to do better than have a good theory, something that is a good standard model gauge, standard model generalization. That stage has not been reached. I think Stacy was here for some time, but he left, I think. Otherwise, he could have commented on it. Yeah. Ashutosh, you want to say something?
Um, Big puzzle, of course. I mean, I have a personal interest query in the experimental sense that one of the signatures, it's sort of a little tangential, Ravi and all, but I'll say it, is one of the experimental signatures that the LHC sort of really cannot trigger on very well. There's a big effort going on to create a trigger for a particular kind of signature, which is a charged particle produced in the collision, which lives or has a lifetime of a few nanoseconds and then decays to dark matter.
Mhm.
Yeah? And so this is called the famous disappearing track signature.
Okay.
If the decay has a very small q value, in other words, you're imagining a charged particle and a slightly lighter neutral,
Mhm.
then in the decay you can get a very soft pion or something that conserves charge, and whatever other quantum number has to be conserved.
Mhm.
But the q value is so small that the visible energy in the decay is negligible. So the only visible signature is that original charge particle parent, which disappears in all practical purposes within a few nanoseconds. Okay? So you only see in your silicon tracker a track which then vanishes. That's why it's called decaying track, a disappearing track. So there's no calorimeter muon signature or anything. So this is not possible for Atlas CMS to trigger on. People are trying all kinds of ideas. We don't even know which one will work. Nothing has worked in the past. To trigger on charged particles only, okay, without calorimeter, without muons,
This,
without anything.
this
So
particle that decays, this particle that decays, does it leave a pion or just everything is dark?
it gives a very soft pion that depends on the Q value of the decay.
Okay.
Could be 100 MeV, 200 MeV, 300 MeV.
And that will
So
not decay to a lepton or something. That's it.
if it decays to a lepton, then it'll have to be a three-body decay with a
I,
neutrino or something as well,
right,
I
right.
imagine.
I
But
see.
even if there was a lepton, some theories I've seen is that the charged particle and the neutral dark matter, let's say, daughter, are
Hmm.
almost degenerate because of some almost perfect symmetry.
Hmm.
Maybe at tree level symmetry and at loop level it's slightly violated or something. Anyway, so the Q value is so small that whatever comes out, pion comes out, a light electron comes out or something, it's all undetectable. So is this worth
There are
trying for?
several.
Because it could be very interesting to build an electronic device which can trigger in real time on such charged particle tracks with no other signature in the detector. maybe pair production. So you can look for two of these. So high momentum track, two high momentum tracks, and then nothing else. Does this fit in plausible things?
That's something that's an idea that I would like to think about, because that sounds quite interesting. Are there so many events like that? Are there many events, or what's the status?
See, if the parent is charged, then Drell-Yang production will give a large cross section.
Mm-hmm.
So we are considering the very exciting possibility that the cross section, the rate is very large, but the trigger efficiency is near zero.
I see.
So you can, just by Drell-Yan production of charged particles, imagine the standard Drell-Yan rate, which is very high.
Mm-hmm.
But if
So
it's untriggerable, then it could be happening right now, and we can't see it. So if there's good motivation for certain lifetimes in such situations, then the trigger design needs to know what the lifetime could be.
that will be interesting to think about some models, I think. That
So
looks
is it related to your?
that I'm not sure that exactly, because I
Okay.
haven't thought about it. But it's certainly possible that in these mirror models there are particles which can decay to invisible tracks. Now, whether they will give a pion or not, that's something I need to think about a little bit. Is there a LHC preprint or something somewhere that one can look at, just to get some details of the signature?
I've seen, what are those called? SU2 left WIMP-like models. So the charged parent and the neutral daughter
Uh-huh.
are almost degenerate because there's an SU2 weak triplet or something
I see.
happening. I mean, you can embed it in supersymmetry or other ways too. This is
Yeah,
where you will be knowing much, much better. But some kind of SU2 left symmetry or something which doesn't, I've heard the following, it doesn't have hypercharge. So one way or the other, it doesn't violate any electroweak constraints or anything.
Mm-hmm.
And because it doesn't mix with the Z, somehow
Right.
this triplet doesn't mix with the Z because the hypercharge is not there. It's pure SU2
Right.
left, something like this.
Yeah, if there is a neutral Higgs triplet, it will not mix with the Z, right?
So okay, now I understand better.
And
Anyway, so
that will be
maybe
interesting.
I don't know which people are pursuing this, but maybe afterwards I can find at least one preprint.
That will be great.
One name comes to mind, Patty Fox at Fermilab, maybe Ronnie Harnick as well.
Okay.
Some combination of those two, but I think Patty has talked to me about this and I understood the logic a little bit.
Okay.
That the
Okay.
pure SU2 weak triplet somehow can be completely acceptable with current constraints and generate a situation like this.
Okay. I'll look at that. Yeah. I can.
And because it doesn't mix with the Higgs, it will, with the Z, it passes all the direct detection of dark matter because there is no single mediator diagram anymore. So it
Mm-hmm.
has to go through a box. I remember this conversation. The
Okay.
charged comes in, switches to the neutral, and then switches back. Sorry, the neutral switches to the charged, switches back to the neutral.
Mm-hmm.
So there are two W mediators,
I
and so it's a
see.
box diagram, and so it's extremely suppressed.
Okay.
And so direct detection will not constrain this, and so this is completely open right now, possible.
Okay. Okay. I'd like to look at that.
Yeah, maybe.
I can track, if you track down real paper, let me know. Otherwise, I can just look at the Paddy Fox and Harnick's web. Yeah.
I don't even know if it was Hardik. Maybe it was. Paddy Fox talked to me at Fermilab about it.
Okay. So I can look at his papers and see.
And maybe other colleagues with him. Yeah.
Okay.
Okay, thanks.
Thank you. Ravi, could you kindly stop sharing? Then we have the full screen for our faces.
Yep.
Yeah. Any more questions, please? Yeah. Yeah. No, I wanted to, since my particle physics friends, you all are here, yeah, I wanted to mention these few things about galaxy rotation curves, which I'm sure you know, but it's good to have this two back and forth discussion. One is, as you know, it is observed that the galaxy rotation curve begins to depart from the Newtonian prediction precisely when the centripetal acceleration goes below a certain critical value from 10 to the minus 10 meters per second square. And this value is essentially universal. It's something very puzzling to understand from dark matter as a new particle point of view. Where does the critical acceleration scale come from? So it is said that, okay, it's somehow contained in the dark matter baryon astrophysics when galaxies are forming. I don't know much about that. Secondly, when the rotation curve becomes flat, the asymptotic will flat velocity is proportional to m to the 1/4, where m is the mass of the galaxy, which is the baryonic Tully-Fisher relation. And again, to my understanding, this is a challenge for dark matter. And third thing, which is very interesting, is as far out we go away from the galaxy, the rotation curve remains flat. Whereas if there was a dark matter halo, the rotation curve would start becoming Keplerian again once the dark matter halo ends. So for me, these are very puzzling features. For me, that looks, at least on the galactic scale, I would have favored the baryonic fifth force, for which it is easy to explain this. On the other hand, dark matter does very well with the cosmic microwave background and with structure formation in the early universe. So I personally feel we are missing something. There is some truth to both sides of the story.
Right. Yeah, I have a former student who is now quite well known in dark matter physics, Haibo Yu, and
Yes, yes, yes.
he has been looking at dark matter with interactions like the mirror model.
Mhm. Yeah.
He tries to fit the galactic rotation curves of different type using this model. So I don't know if I'm not
Yeah,
sure.
no, so since we are with friends, I can ask you, is it that this whole issue of dark matter versus mon also a community or a sociological thing? Particle physicists, I see, want like to have a new dark matter particle because,
Right.
that's what beyond standard model physics is.
True.
And we might look for it at the LHC or other, or, the sort of non-accelerated detectors. And whereas there is a community who says, because fitting galaxy rotation curves with just baryons is very straightforward once you change the law to the
Mhm.
Moore law, that fit is very insensitive to the presence of dark matter. The fit is so good that one asks that if dark matter had been there, it would have played some role in the fit. But with baryons, as Stacy Mega would tell us, the fit is very good just with baryons. So extremely puzzling that
That's true.
we we
No,
don't
no.
s-
Yeah.
we don't
Yeah.
see signs of dark matter when we do this fit. On the other hand, I agree. What puzzles me greatly is that if it's a fifth force, its Coulomb aspect does not fall as 1 by r square. It falls as 1 by r, which is extremely puzzling, which is what I think makes some people unhappy with MON. If it's a standard model gauge theory like U1, the electrostatic analog field should fall as 1 over r square. But it has to fall as 1 over r if it has to dominate
Mhm.
gravity out. So we try our uh, hands around that, but it's a challenge. I agree, if it's a fifth force like Mon, it has to be really shake up a lot of fundamental
Oh,
physics.
yeah. No
Yeah,
question about it. Yes.
yeah. It's not a ordinary U1. It falls as 1 by R, and
Yeah.
it would shake up fundamental physics if it's if it's of ordinary, if it's a fifth force between baryons, undoubtedly there will be some very profound extensions of general relativity.
Sure.
And maybe that's what keeps particle physicists skeptical about. It's much more conventional to have a new particle than to, shake up the laws of physics. Yes, I agree. But again, on the galactic scale, it's new law seems to work well. I call it, we call it Kepler's laws. Kepler's laws for the solar system, Kepler's laws for the outer regions of the galaxies. So we have these Kepler laws, but we don't know um, what is the underlying analog of Newtonian
Right.
gravitation.
Yeah, I think it will be nice to think about it and see if one can arrive something.
Mhm. Yeah, dark matter for cosmology and MON for galaxies, and
Right.
some union of
Could be some mixture, yeah.
yeah. Yeah, Ashutosh, I've seen you have kept quiet on the MON. You don't express yourself
Oh, on
on
Mond?
yeah. I would like to know your reservations.
Uh, you're asking a theoretical question,
Mm,
which I don't know if I can comment intelligently. Um, Let me put it this way. I have bigger reservations about dark energy than dark matter
mm,
particulate. Okay. What do
mm.
I know? I know that, i- what do I know? It seems that it is relatively easy to produce particulate dark matter. Yeah. I mean,
Yes.
my simple mindset is if you roll back the clock 100 years, then even something that we now consider straightforward, like a neutron proton, so the neutron, unless you have pretty good detection techniques, the neutron, which is almost equal numbers or more than protons, the neutron is dark, is almost dark.
Yes,
It
yes.
took a long time to detect neutrons because they have mass, they bounce around, but unless you can detect recoil or whatever it is that somebody, Chadwick, discovered neutrons somehow, it's not easy. I mean, neutron and positron detection came about the same time, like
Mm,
much, much later than proton and electron,
mm,
which gives you some sense, you know, that positron is a huge deal, and
mm,
detecting it and making it or finding it was no harder than neutron. So it gives
mm.
you a sense that neutron feels pretty dark unless you really have
I,
modern techniques and if you roll back 100 years. So and now we would argue that a neutron is very easy to make. It's a very
mm,
simple logic that we understand completely how neutron is made. And it was almost dark. So
mm.
if I extend the same logic to some neutral symmetry related partner, to something that embeds in the standard model very easily,
Mm.
like this SU2 triplet, SU2 weak triplet, or you make up whatever, then particulate dark matter is almost expected. Why should we think that our particle spectrum is complete? Over
No,
200
I agree. I
years, it
agree.
has not been
Uh,
complete. It
yeah,
keeps
yeah, yeah.
growing. Every time we realize,
I
oh, there
agree.
is one
I
more
agree.
thing, keeps growing.
I
So,
agree.
in this sense, and since the Big Bang is roughly infinite energy to produce everything that is
Mm,
in the spectrum of field theory, it's not so necessary to do MOND. It's rather easy to just invent a little
yeah, yeah.
extension to standard model and
I
make a
agree.
more particle,
I
right?
agree.
And completely fits with quantum field theory, doesn't
Yeah,
violate
yeah,
naturalness, it doesn't violate
yeah.
any. Compared to that, I keep seeing dark energy evidence is, I would say, more nebulous
Yeah, yeah, yeah. I
and
agree. Yeah.
and has deeper issues with space-time and all this, right? You know, all this.
Yeah.
So I would say if you ask me to argue for MOND or against particulate dark matter, I don't know. Could be this, could be that equally. Maybe particulate dark matter is actually easier than MOND.
Yeah.
But
No, I agree that
dark
the
energy is all over the place. So
yeah, yeah, yeah. Yeah, yeah. Yeah, suppose we leave out dark energy for now. We that's another discussion. I'm saying the fact that dark matter particle has not been discovered experimentally yet cannot be a good reason for saying claiming that it does not exist. No,
agreed.
not that. Not that. I fully am with you and Ravi on that. But the properties of galaxy rotation curves for me are very striking. You know, like this critical acceleration scale is the hallmark of a fifth force. Below this acceleration, the fifth force becomes more important. And similarly, you know, extremely the rotation curve staying flat, getting very, if you give me the baryon distribution of a galaxy in terms of stars, I can predict the rotation curve as if the dark matter doesn't exist. So these are the things that are bothering me, you see, that it seems that on the galactic scale, MON, even though MON is just phenomenology, it's Kepler's laws, it's on the galactic scale, it seems very natural to have a modification of gravity, whereas on cosmological scales, it seems very natural to have a particle dark matter, which is collisionless. And there is something I feel more to it than just saying particulate dark matter, where I mean, there would be, I wish there were more experts here on dark matter, astrophysics, and rotation curves. But they put it as that these are complications of dark matter baryon hydrodynamics, which we don't understand well. But like if Stacy was here, he would, like he said in his talk, he would point to various features of how well MOND fits on galactic scales. It's like he says, why does MOND even work? Why does it fit galaxies so well? That I think is the crux of the matter.
You know what I can suggest is
Yeah.
try to get this person, Haibo Yu.
Okay. Okay.
He's doing all dark matter fields with self
Okay.
interact.
Maybe we can have a talk from him. Yeah. I will
Yeah,
look up. How was the last name? You, is it? YU, right?
YU. Yeah, he's at the
Oh,
University of California, Riverside.
okay, great. Yeah, I know the name. Thanks for suggesting. Yeah, it will be
Yeah,
good to listen to him and understand how they are fitting galaxy rotation curves with
yeah, yeah.
matter.
Especially he's doing that lately with several of his colleagues. You know, how
Mm-hmm.
to understand the galaxy rotation curves in the dark matter with self interaction.
Okay, okay, okay. Yeah, great. Very
Okay,
good.
great. Thank you, Tajinder.
Thank you, Ravi. Great to have you with us. So, just I think there's any other comment. Yeah, no, I think we are done. So we'll meet. Thank you, Ravi, for being with us for so long and sharing the discussion. Really appreciate it. And yeah, and we'll see you all in 2 weeks from now, May 30th. Roya Mohaye, sorry, I don't know how to pronounce the last name. Roya Mohaye from France. She'll talk on challenges to the standard model of cosmology. So
Okay.
that probably tie in an interesting way with your talk today.
Yeah, yeah,
So
sure.
let's close the session. I'll say bye to all of you and close the session. Thank you very much.
Thank you.
Bye
Thank you.
bye.